briefly review that the y equals sine x has these 5 key points. The zeros occurring along the x-axis at 0 degrees, 180 degrees, and 360 degrees. Halfway between two zeros is the first max at 90 degrees, and halfway between the second zero and the third zero is the minimum at 270 degrees. The period of the function is how many degrees it takes for one wave, which is 360, or in radians 2 pi. Let's work to establish what y equals cosine x looks like, or why it looks like this. You can see it's kind of similar, and if I was to continue, it's sine wave also, but shifted, right? So let's see why we've got this. The period is 360 as well, because from 0 to 360 we get from a peak to a peak, or a max to a max, 360 degrees for one full wavelength. You'll notice that the zeros are in different places. The zeros for cos are where the max and min were for the sine. Okay? And it all just comes from graphing using, start a table of values if you want to know where these come from. X and cos x. If x is 0 degrees, the cosine of 0 is 1. So there's the point, 0 degrees, 1. Let's do 30 and 60 as well, like we did before. So 30 degrees, and the cosine of 30 is 0.8660. That's up here. 0.8660. And 60 degrees. And the cosine of 60 is 0.5. That's kind of equivalent to quadrant 1, right? 0 to 90 is quad 1. From the cast rule, just think that. What quadrants is cosine positive in using cast rule? We talked about it briefly, I think, together, but you might have done this in last semester. So cast rule tells us where a function is positive. And cosine is positive where they're all positive, and it's positive with the c. So it's positive in quadrant 4 as well. And look where it goes up above 0. Quad 4. That means it's negative in quad 2 and 3. And it is negative. It goes down below the x-axis. Okay, I'm just trying to tie things that you've seen before into why the graph looks like this too. If x is 90 degrees, we know that the cosine of 90 is 0, so we get a 0. And the same things, the same patterning if I do 30, 60, 90, okay? And you don't have to do 30, 60, 90, you can do any angles. I just wanted to show some specific ones. So the other one was the snake, right? Because it was a wriggly snake doing this with. And what does the cosine one look a little bit like? You can see the red nose, the black eyes, And the blue on the tip, sorry, not black. The blue on the tips, this is the puppy. Okay, so we have a snake and a puppy. If that helps you to remember it and it's kind of silly, feel free to use it. I had a student say it to me one time, and I thought, wow, you know what, whatever works. Okay? If you see it, some people don't see it, but if you see it, that's fine. So that's y equals cosine x. The coefficient here is a 1, which is the amplitude of 1. And the multiple in front of x here is a 1, which means one wave length in 360 degrees. And it repeats, it's periodic, it repeats every 360 degrees. Those are the two functions we will do the most manipulation with, because now, once we get used to those, we're going to be changing the amplitude, changing the wavelength, and changing the period. And shift side to side too. Changing the wavelength and changing the period are kind of the same thing. Then we'll make shifts of them as well. We'll slide them left and right. In terms of graphing them, it's really important to know, or it's helpful to know the key points and that they're evenly spaced. Okay, so halfway between a max and all the time. I'll refer to that later when we get doing some more graphing on it. So here are the basic features of the graphs of y equals sine x and y equals cosine x. And they are in the textbook. They're also in these posted notes. So you don't have to write the whole thing down right now. Leave a little gap for these 7 points if you want to fill it in a little bit later. But I'll just talk about them. For y equals sine x and y equals cosine x. Now I told you they were periodic. That means they are repeating, right? Or like the same process repeats over and over and over, periodic. The domain is the set of all possible x. Well, what values of x can we find the sine and cosine of? And it is all values of x, all real numbers. The range, that's all possible, the set of all possible y is, it goes from -1 to +1, right? We saw that on the graph. The y values from -1 to +1 doesn't go beyond that. So the range is the set of all y's, -1 to +1. The amplitude is half the distance between the max and the min. So it's a 1. Since the distance between -1 and +1 is 2, the amplitude is half of that, which is 1. Both graphs are exactly the same, and we call them sinusoidal. The graph of the cosine curve is shifted pi/2 or 90 degrees to the left of the sine curve. We call that a phase shift. They are phase shifts of each other. For both graphs, the values of y repeat every 2 pi units for x, or 360 degrees. We therefore say that the functions are periodic with a period of 2 pi or 360 degrees. You can do it in radians or degrees. The functions have zeros, maximum values, and minimum values. And these are key points that we will use to graph later. So the key points are important to know where they are. The functions have zeros, maximum, minimum values, and minimum values when x is a multiple of pi over 2. That is when x is a quadrantal angle. Quadrantal angles are angles that lie on the quadrantal axes. So 0 degrees, 90, 180, 270, and 360. The behavior from 0 to 2 pi at these values is summarized below. So the key values, but for y equals sine x, sorry, for 0 first, the sine of 0 is 0, pi over 2 or 90 degrees is 1, pi, which is 180, it's back to 0, 3 pi over 2, which is 270, it's minus 1, and 2 pi, which is 360, it's back to 0 again. And notice what cos does. Same numbers, different order. Okay, so that's a summary of them. When one value's on a 0, the other one's on a max or min, and vice versa. So the period, this is pointing at the cosine one in pink. The period is 2 pi. The amplitude is shown there, or half the distance between a max and min. And that this key point of min right here is a difference of pi over 2, so a shift. If I take my minimum value on the sine curve and shift it left pi over 2, I get to the minimum of the cosine. Each value, if I take my 0 here on the sine curve, shift it pi over 2, I get to the 0 on the cosine curve, and so on, all of them. Okay. And just leave that a moment in case you're writing it down. Okay, let's see. So let's make a slight change to y equals sine x. Now we are going to look at graphing y equals a sine x. That's a general equation for changing of amplitude. That's the first alteration we're going to make on y equals sine x. And we will look at y equals 2 sine x. So the amplitude is now changing from 1 to 2. And if you notice the order of operations, first you would take the sine of x and then you would multiply it by 2. So for example, remember pi over 6, which is 30 degrees. It was 1/2 times 2, which is 1. And that's why we're at 1 there. And the 60 degrees, or pi over 3, is 0.8660. If we multiply that by 2, is 1.7. And that's up there. And for 90 degrees, it was 1. If we multiply by 2, we're at 2. The period is still 2 pi, or 90 degrees. But it's been pulled at the 90. Pulled down at 270, and but it still maintains that same wavelength. Notice something about these. They don't do this. This is not a graph of a sine wave, okay? These graphs, I want you to realize, when they're closer to 0, we'll just do it like this. So 0 and 360. 180. When they're closer to 0, they okay, so just don't draw them as pointed graphs. They're not. They're flatter at their maximum and minimum, and they're more steep near the zeros. All right, what do I have down here? Okay, plotting y equals a cos x. Now this one, because cosine x is good, we need to know the cosine x before anything has happened to it, okay? It looks like that. 0 to 360. If we take every single value on there and multiply it by -3, first, it's going to stretch it by a factor of 3, and then flip it to the negative, won't it? So it's going to take this value of 1 and turn it into -3. And it's going to take this value of -1 and turn it into, I should have pulled that up here, +3. Can put it up there. At 0, 0 times -3 is still 0. So it's going to go. That's where I say we use these key points to draw the graph. And there it is, done. You can see it down there. On my graph, I have it compared to cosine before. So let's put cosine before anything happened to it. A little better than that. I can do better, sorry. -1's there, +1 is there. All right. There. You see how it got stretched by a factor of 3 and flipped. Like the x-axis is the flipping point, okay? The mirror. So that's what a change in amplitude does to the function. And that's where we're going to stop for today, because next we talk about changing the period. But we will do that next time we talk about these things together, okay? Which will probably be in 2 weeks. I might leave you some notes to look at in advance, but I will begin here in 2 weeks, week 10. Next week is your test. Okay, so remember that you begin the test at noon. I will let you know then how long you have for it. Make sure you submit by the time the test is done, the indicated time on the test. And if you have any issues with your upload, send them by email. But don't everybody do that, okay?
You're talking about the test or something?
Yes, I'm talking about test next week.
Okay.
Next Tuesday, next Wednesday at noon, right? Because your Wednesday class, 12 o'clock noon, test 2. That's all you have to do for math next week, test 2. And that's it.